Right now, part of your body is younger than the rest of it. Not by feeling, and not by chance, by physics. Your feet sit closer to Earth's mass than your head does, and that changes the pace of time between them. Gravity isn't a force pulling you down. It's a curve in the fabric of space-time itself. The deeper you sit inside that curve, the slower your clock runs. Your head sits about 1.5 meters higher, in slightly weaker gravity, so it ticks forward in time microscopically faster. The gap is real, measured in laboratories with lasers precise enough to see it. It amounts to billionths of a second across a lifetime, but it is there every moment you're alive. You are not one age. You are a gradient of ages, stacked vertically, from ankle to scalp. Every second you stand upright, your brain edges further into the future than your feet do. This isn't science fiction, and it isn't a rounding error. It's the same physics that keeps GPS accurate to your exact location. By the end of this video, you'll understand why simply standing up stretches you, in a literal sense, across time. To understand why, go back to 1907, 2 years after Einstein published Special Relativity. He was at his desk in the Swiss patent office in Bern when what he called the happiest thought of my life arrived. He imagined a man falling freely from a rooftop, realizing that inside the fall, gravity would seem to vanish entirely. Acceleration and gravity, Einstein realized, are locally indistinguishable, the same phenomenon seen from different angles. Stand in a windowless rocket accelerating at 9.8 meters per second squared, and you cannot tell it apart from standing on Earth. This is called the equivalence principle, and it became the foundation for everything that followed. If acceleration can mimic gravity perfectly, then gravity itself must be baked into the structure of space and time. In November 1915, Einstein presented his field equations to the Prussian Academy of Sciences in Berlin. The equations describe how matter tells spacetime how to curve, and how that curvature tells matter how to move. At the theory's heart is the metric tensor, a mathematical object measuring distance and duration at every point in spacetime. Near a mass like Earth, the tensor shifts, space compresses, and time slows, relative to empty space far away. This isn't a metaphor. The tensor's numbers shift measurably as you move closer to, or farther from, a planet's mass. The stronger the gravitational field, the closer you are to the mass, the more the time component shrinks. This is gravitational time dilation, and it applies to every mass in the universe, from a marble to a star. Even Earth, an unremarkable planet, warps spacetime enough to be measured to 1 part in a quadrillion. For 4 decades after 1915, nobody had a clock precise enough to actually see it. That changed in 1959, when Harvard physicists Robert Pound and Glenn Rebka built an experiment inside the Jefferson Physical Laboratory's tower. They didn't use clocks. They used gamma rays from radioactive iron-57, exploiting the Mossbauer effect for extraordinary precision. The tower was 22.5 meters tall, barely the height of a 7-story building. General relativity predicted that light climbing out of a gravitational well should lose energy, its frequency redshifting slightly. The predicted shift was about 2.5 parts in 10 to the 15, small enough to seem absurd to even measure. They detected the shift, and it matched Einstein's prediction to within about 10%. Later refinements by Pound and his student Joseph Snyder in 1964 brought the agreement to within 1%. It was the first lab confirmation that gravity slows time, over a height smaller than most apartment buildings. It proved that time dilation isn't reserved for black holes or neutron stars. It happens on the scale of a staircase. In 1976, NASA physicist Robert Vessot pushed the test further in an experiment called Gravity Probe A. A hydrogen maser clock launched nearly 10,000 kilometers into space, compared continuously against an identical clock on the ground. At the peak of its trajectory, in far weaker gravity, the rocket's clock ran measurably faster, exactly as predicted. The next major test, in 1971, involved commercial airliners instead of towers or rockets. Physicist Joseph Hafele and astronomer Richard Keating flew 4 cesium-beam atomic clocks around the world, once eastward, once westward. Back on the ground, reference clocks sat at the U.S. Naval Observatory in Washington, D.C. When the clocks landed, their times no longer matched the ground clocks, and the mismatch wasn't random error. It was 2 relativistic effects combined, velocity time dilation and gravitational time dilation from flying farther from Earth's mass. The eastward clocks lost 59 nanoseconds. The westward clocks gained 273, both matching Einstein's equations almost exactly. Published in Science in 1972, it became the Hafele-Keating experiment, one of the most cited human tests of relativity. Part of that came purely from altitude. The plane sat roughly 9 kilometers up, in measurably weaker gravity. Nobody on board felt it, just a number, permanently recorded, proving their personal clock had shifted. This same effect now runs underneath a system you likely use every day: GPS. GPS depends on satellites, each carrying an atomic clock, orbiting about 20,200 kilometers above Earth. At that altitude, two effects compete. Velocity slows the clocks about 7 microseconds a day. Weaker gravity speeds them up about 45. The net result? GPS clocks run about 38 microseconds a day faster than clocks on the ground. That sounds negligible, but GPS calculates position from radio signals at light speed, where nanoseconds become meters of error. Engineers correct for this before launch, slowing the clock's frequency so orbit brings it back in sync with the ground. Every GPS satellite, in other words, is built with Einstein's equations already programmed into its hardware. Without this correction, your phone's map could place you in the wrong city within a single day. But the most striking demonstration wasn't in orbit. It happened on a tabletop, in a lab in Boulder, Colorado. In 2010, physicists at NIST built 2 aluminum-ion optical atomic clocks, among the most precise instruments ever made. Publishing in Science, they showed the clocks could detect time dilation from a walking pace velocity difference. Then, they raised one of the clocks by just 33 centimeters, about 1 foot, relative to the other. The elevated clock ticked faster, exactly as predicted, by roughly 4 parts in 10 to the 17. A single foot of elevation, over a lifetime, separates 2 clocks by tens of nanoseconds, the gap between your ankles and knees. 12 years later, in 2022, a team at JILA, led by Jun Ye and Tobias Bothwell, pushed the measurement further. Publishing in Nature, they used strontium atoms cooled to near absolute zero, held by lasers in an optical lattice clock. Rather than 2 separate clocks, they measured the ticking rate difference across the top and bottom of 1 millimeter of atoms. They detected a measurable difference in time flow across a single millimeter, roughly the thickness of a fingernail. It's real between a tabletop and a shelf, and real between the top and bottom of a grain of rice. Your body, standing upright, spans roughly 1,700 of those millimeters from heel to scalp. To see this effect at its extreme, you don't need a human body. You need a black hole. Near a black hole's event horizon, gravity becomes so intense that time, to a distant observer, appears to slow to a crawl. An object falling toward that horizon would seem, from far away, to freeze forever, though it falls through instantly from its own view. It's the same equation Pound and Rebka tested on a tower, and NIST tested across 33 centimeters, just multiplied by an incomprehensible gradient. Astrophysicists have measured this near the supermassive black hole at our galaxy's center, Sagittarius A star, using orbiting stars as natural clocks. In 2018, astronomers using the Very Large Telescope tracked a star, S2, sweeping near it, confirming the redshift Einstein predicted a century earlier. The physics governing a star swinging past a black hole is, mathematically, identical to the physics governing your own scalp and heel. Only the strength of the gravitational field changes. The equation itself never does. So what does the equation actually say about you, standing in your kitchen right now? Physicist Richard Muller, in his book, Now, The Physics of Time, calculated the effect for an average human body. Your head sits roughly 1.7 meters higher than your feet, and gravity weakens slightly with altitude. Over an average 79-year lifespan, that difference adds up to roughly 90 nanoseconds. Your head, across your whole life, ends up about 90 nanoseconds older than your feet would be, had they lived it independently. 90 nanoseconds is roughly the time light takes to travel 27 meters, about 2.5 school buses. It's too small to feel or matter, but not too small to measure, or to be true. To be precise about what this doesn't mean, this isn't biology finding a fountain of youth in your toes. Time dilation doesn't slow aging's chemistry or cell division. Every process proceeds identically regardless of clock rate. This is what unsettles physicists. The difference isn't biology. It's a property of space-time itself. This same principle explains why someone on a skyscraper's top floor ages, imperceptibly, faster than someone in its basement. It explains why ISS astronauts, 400 kilometers up, get a mixed result. Speed slows their clocks, altitude speeds them up, and speed wins. Over a 6-month mission, an ISS astronaut ends up younger than people on Earth by roughly 0.005 seconds. But they aren't hypothetical. They're logged, calculated, and cross-checked by physicists whose job depends on getting them right. Every time you climb a staircase, you shift your body, by a measurable amount, into slightly faster time. Every time you lie down to sleep, you flatten that gradient, head and feet drifting back toward the same rate of time. Standing up, in other words, is a small, silent act of time travel toward the future, for your head more than your feet. Think about the last time you stood up out of a chair. In that single motion, you didn't just move upward. You measurably changed how fast time passed for different parts of you. Every step you've ever taken has stretched you, ever so slightly, into a different pace than the ground beneath your feet. You have never, for one instant of your life, been a single age all at once. You are not a point moving through time. You are a shape, and every part of it experiences a slightly different present. This is not a flaw in the universe. It's the universe refusing to grant even one body a single, uniform now. Einstein spent his last years making peace with what his equations implied. The present moment isn't something nature provides. There is no universal clock keeping the cosmos in sync, only your local patch of space-time, running at whatever rate mass dictates. The you, who exists right now, is really a stack of near-identical yous, layered from heels to scalp, each slightly ahead or behind. It's a strange kind of privacy, a fact about your body not even you can perceive, one no one before Einstein imagined asking. Somewhere in a lab in Boulder, Colorado, a cloud of strontium atoms the width of a fingernail is proving this again, right now. Somewhere above you, satellites correct for the exact same effect, just so a stranger's phone can tell them which street they're on. None of it changes how your day will go, or shows up in a mirror, a heartbeat, or a memory. But it means the simple act of standing at full height is, in the most literal sense, allowed, an act of spreading yourself across time. You are not just a body occupying space. You are a body occupying duration, unevenly, imperceptibly, but really. Your feet are anchored a fraction deeper in the gravitational well of the only planet you've ever called home. Your head reaches, by the smallest measurable margin physics has confirmed, a little further into what comes next. Somewhere between the two, carrying both, is you, not frozen in a single instant, but stretched across the fabric of time. The next time you stand up, you won't feel it, but for a billionth of a second, you will be a little more than one age. You will be, quite literally, more than the sum of a single moment.